how's it going, everybody? We are here. I'm making this video on Monday, April 12th, and today we're going to talk about section 3.6, which is going to be about second order differential equations. Really importantly, you should notice that this is a section that's falling within a chapter that's discussing systems of linear equations, and so this should seem a little bit out of place. However, what we've definitely seen in the last few weeks is that we've been able to solve all of our second order differential equations that we've seen so far using just our techniques from our systems of linear differential equations. And so we kind of want to formalize that relationship a little bit today, and then come back to talking a bit about the physics background behind why. Remember, you should be asking yourself, when was it that we even started talking about these second order differential equations? What was the physics discussion that was happening there? We'll come back to kind of talk about that a little bit more here today. So I think that what you'll find is that today is going to be, I don't know, I think the math is a little bit easier today. Honestly, I guess what I can definitely say is I think that sections 3.2, 3.3, 3.4, okay, sorry, 3.3, 3.4, 3.5 are real distinct eigenvalues, complex eigenvalues, and then repeated and zero eigenvalues. Those three sections, that's a lot of stuff. That's like three of the toughest back-to-back sections that I teach in like any class right there. It's a lot of math that's been going on there. I think that this one's a little bit of a break from that. I think that we've hit kind of some of the hardest sections that we're going to see there. We'll see some tougher stuff later, but it's all going to be based on the fact that we already learned that stuff here in chapter 3. So that's honestly some of the tougher stuff that I think that we do in this class here. So again, what we're going to see today is a bunch of relationships that we've already seen. We're just sort of formalizing them and then having a little bit of a physics discussion here today. So every second order differential equation that we've seen has been solvable as a linear system, right? So we're talking about our second order differential equations here. We've got a second derivative, a first derivative, and a zeroth derivative right there. So in general, we refer to these guys as homogeneous, constant coefficient, linear second order equations. As we've seen, we get like all of these adjectives that go on this. So let's talk about each of these words real quick. The word homogeneous here is telling us that all of the parts are well mixed, which really means to me I've mixed together all of the components of this equation onto one side. I almost feel like this is like the opposite of homogeneous, or I don't know. I feel like this is always like a little bit of a weird word right here, but it's saying all the components are mixed together on one of the sides, so it's separated. So basically homogeneous is basically a roundabout way of saying is that it is an equation that everything's on one side, meaning that there's nothing on the other side, that it is an equal to zero equation. So homogenizing all of your parts puts everything on one side right there. You should notice that so far we've only talked about having constant coefficients, but it's absolutely the case that there's lots of meaningful differential equations out there. In fact, most meaningful differential equations out there have our parameters A, B, and C, or in our A matrix, our A, B, and C being actually functions of time rather than being constants out there. So constant coefficient, A, B, and C are all constants for now. This word linear right here is sort of like, I don't know, in a sense almost misleading, but this word in here, linear, is referring to it can be written as a first order linear system. So that's kind of a weird, sneaky word to call this a linear second-order differential equation. What that really means is that it can be written as a first-order linear system rather than a second-order equation right there. So that's what we mean when we say linear. Second-order, obviously, just meaning that there's two derivatives in there. So this is like the long-form fancy name for these things that we've been looking at: a homogeneous constant coefficient linear second-order differential equation. Such a mouthful right there, but all those individual adjectives are not too terrible to pick apart right there. So we've been solving these, and it turns out that we've had two different techniques for solving these. We solved this differential equation once in chapter 2, and we have solved it since then in chapter 3. I'm going to write as fast as I can and do all this math right here since we've already seen both these, but I do want to kind of, again, today is sort of our bringing it together for our second order stuff here, so I do want to see all these parts here. So one of the ways that we've done this, the chapter 3 technique, is to rewrite as a system and to use linear algebra. And then we will do our chapter 2 technique. Guess and fill in the blanks. This is what we did the first time we solved this thing right here. So I'll do that guy second here. So what do we do in chapter 3? In chapter 3, we said, well, we can solve this by converting it to a system and then doing our eigenanalysis here. So we're taking our x double prime plus 7x prime plus 10x equals 0. And I want to say to myself, well, it's hard for me to talk about position when it's defined in terms of acceleration without also talking about velocity. So we said, let's define a new variable for ourselves. And let's say that the derivative of position is velocity. So dx dt we're going to call v. Then we said we can take the derivative of velocity, and that should be acceleration. Importantly, remember, dx dt is the same thing as x double prime, right? That's the derivative of velocity is acceleration, the second derivative of x right there. The second derivative of x, I can solve for in this equation by subtracting over these two components to the right-hand side. So that should be giving me a negative 10x. Right, negative 10x, and then a negative 7, that's v right there. The derivative of x is what we're calling v, so that should be a minus 7v that we got from this guy, and that led us to having this A matrix of consideration of 0, 1, negative 10, negative 7. Right. From here, we were able to do the linear algebra math that's associated with this thing right here. So we're going to find our eigenvalues by taking our determinant of a minus lambda I and setting it equal to 0. And that's going to give me negative lambda 1, negative 10, negative 7 minus lambda. The determinant of this should be equal to 0. That gives me lambda times lambda plus 7 plus 10 is equal to 0. That's lambda squared plus 7 lambda plus 10 equals 0. That's going to give me lambda plus 2, lambda plus 5, and we're clearly getting here that we're going to get lambda equals negative 2 and negative 5. Now I can go ahead and plug these things in here. So 1 is our eigenvalues, and then step 2 is our eigenvectors. So now I'm going to say, let's let lambda be equal to negative 2. And in this case right here, I'm using my A minus lambda I matrix times a vector v. The eigenvector should be equal to 0. And so I'm seeing here we're going to get a positive 2, a 1, a negative 10, and negative 7 minus negative 2 is going to be a negative 5 right here. We can tell that we did this correctly because we have this redundancy from one line to the next. Having a 2 and a 1 as the coefficients on x and y is equivalent to having negative 10 and negative 5, given that our output is going to be 0 on the other side over here. It seems to me like a good xy choice in this case would be to allow x to be 1, so we get one copy of positive 2, and let y be negative 2, so we get negative 2 copies of 1. That way positive 2 and negative 2 give us 0 there. So I think this is my good first eigenvector. We'll call that lambda 1. Then we look at lambda 2 being equal to negative 5. A minus lambda I, using this matrix right here, is going to be positive 5, 1, negative 10, and plugging in negative 5 there gives me negative 2. And again, we notice the redundancy in the two rows right there, that they're giving us the exact same pieces of information. We find that a possible vector that could be our solution right here. I think I'm going to do basically the exact same thing. I'm going to let x be 1, so we get one copy of positive 5. I therefore need negative 5 to cancel it, and so negative 5 copies of 1 will do that for me. That'll be what I call my vector 2 right here. And so we've got all the parts that we need to build our general solution. So our general solution based on this should just be our y of t equals k1 e to the lambda 1, which is negative 2, t, times v1, which is 1, negative 2, plus k2 e to the negative 5 t, 1, negative 5. And there we go. We got our general solution. So this is what we've been doing for chapter 3. What we want to see is that this is equivalent to what we did in chapter 2. And what we want to do is we want to kind of formalize that we're always going to get this nice relationship between these guys here. So we solved this before we knew how to do any of our eigenanalysis, right? And what we did is we said, listen, if there's going to be any function that's actually going to result in all of these terms canceling out and going to 0 together, what we need is that the first and the second derivatives have to have the same components as one another, right? The 0th, the first, and the second derivatives all have to be kind of the same function to cancel. We asked ourselves, hey, could this be like a polynomial? And we said there's no way. If x was a polynomial, then the highest degree term in x wouldn't exist in x prime or x double prime because they're all going to be 1 degree lower, and there wouldn't be anything to cancel away the highest degree term that was associated with x. We asked if this could be like, we looked at a couple different families of functions and kind of ruled all them out as possibilities there because we would need all of our terms to cancel and go away. The possibilities that we saw were that this could be some like trig functions because sines and cosines are always what we're going to get from our first and second derivatives. We also saw that some of our possibilities here were exponential functions, right? Because like e to the 2t, you take the derivative, you get back more e to the 2t, and so it's possible that all those terms could end up canceling each other out then. So what we did here when we did this guy back in chapter 2 is we said, let's guess that our solution would be x of t being of the form e to the, I think that we used the letter, I'm looking at my notes here, e to the pt, right? This was our guessed solution for this thing right here. And so if that were the case, then we'd want to find that x prime of t is p e to the pt, and x double prime of t would be p squared e to the pt. We go and we plug this stuff into the differential equation, and what we find is that x double prime plus 7x prime plus 10x equals 0 is going to lead us to p squared e to the pt plus 7p e to the pt plus 10 e to the pt equals 0. We can factor out this e to the pt and see that we're left with p squared plus 7p plus 10. Oh my gosh, it's the same quadratic that we landed at in terms of lambda over here. Not surprising to me based on what we've been doing for this last week. And so here we find that this is p plus 2, p plus 5 equals 0, and that's going to lead me to p equals -2 and -5. So that tells me that x of t equals e to the -2t, and x of t equals e to the -5t are both solutions. And then by the linearity principle, we get a general, so I'm going to call this x1 of t and x2 of t. By the linearity principle, we're going to get a general x of t to be k1 e to the -2t plus k2 e to the -5t. Now, what I was claiming is that these solutions were going to be equal to each other, but you should notice that there's still a little bit of a distinction. This solution right here involves our description of both the variable x and the variable v, whereas this guy only includes our description of x. However, you should notice that if you only look at the top components of each of these two vectors, they do perfectly match. This is k1 e to the -2t times 1 plus k2 e to the -5t times 1. That's exactly what we got right here for x. So this does match the top. The question is, does this also match the bottom right here? And I think that we can keep on going. So to get the system solution, v of t equals x prime of t. And so we're going to end up getting that our x of t, v of t, v is just the derivative of our x stuff out there, right? So what we're going to end up seeing here is we're going to go ahead and we're going to get our x solution is just exactly what we wrote, k1 e to the -2t plus k2 e to the -5t. And if I go ahead and take a derivative, I'm going to get a -2k1 e to the -2t minus 5k2 e to the -5t. And we can relatively easily see that this is the same as this guy over here. We've got our -2 coefficient, we've got our -5 coefficient, or maybe I should say, you should notice that this has the overall coefficients of 1, -2, and 1, -5, and there's our 1, -2, and 1, -5. So the whole important point of this right here is that these clearly are exact matches of one another right here, right? So those are equal to each other, these two solutions that we got right there. So what we want to do is we want to kind of prove that one of our that this guess was actually correct right there. And the thing that I'm kind of thinking to myself is I think that the thing that we kind of really want to see for ourselves here is that this characteristic polynomial equation that was right here is clearly matching our coefficient polynomial that we came up with the p's right there. Those two things were obviously the same, leading us to the key components of our solutions here, which is those coefficients of -2 and -5. So let's go ahead and check out that in general, this is always going to work out this way, right? We're saying one of those two solutions may be a little bit easier. I don't feel like we needed to get into all this like convert to a system, finding matrices, finding eigenvalues, all this stuff. I kind of feel like we could have just made the jump straight from this differential equation straight to this box in red. I feel like that should have been an easy jump that we should be able to make right here, since the coefficients are the same of 1, 7, 10, 1, 7, 10, 1, 7, 10. We want to show this is in general true, so we can start skipping some of our work right here, right? So let's go ahead and do this in general. If this is my general differential equation, then I'm going to start with my same first step here, which is to say, oh my gosh, I'm going to write dv every time. I want to say dx dt. I'm defining that to be v. And then our dv dt, well, we should see here that we can write this as like ax double prime is equal to -bv minus cx. And so x double prime should be, and I'm going to write this as -c over a x minus b over a v right there, right? And again, I called v x prime right there. So it seems like that's going to be my helpful way to write dv dt, since dv dt is really x double prime. It looks like it's going to be -c over ax minus b over a v. And so that should lead me to an A matrix here of 0, 1, -c over a, and -b over a. This should generally be the A matrix for every single second order differential equation that you ever convert to a system. I'm going to put it in a box right now because I'm going to want to come back to reference this formula later. One of the reasons why this is a practical thing for me to remember right here for these coefficients, this is our relationship between the second order equation and the system. The reason why this is valuable to me is because I often want to graph solutions to second order equations, but our graphing stuff that we all set up is based on an A matrix. So when I go to use my Python code later today, this is the structure of stuff that I'm going to want to throw in. So we'll scroll back up to see this again later right here so I can reuse these parts. The point is, I want to prove that this is always going to have the correct characteristic polynomial to match our coefficients out here. So let's go ahead and look at our determinant of a minus lambda I and set it equal to 0. When I do this, this is my determinant of negative lambda 1, -c over a, -b over a minus lambda. And I'm claiming that that should be equal to 0 if we're going to get our solutions for lambda here. So it looks like I can do lambda times lambda plus b over a plus c over a is equal to 0. And if I go ahead and try and solve this thing, I'm going to get lambda squared plus b over a lambda plus c over a equals 0. And I'm just going to multiply the whole thing by a, and we're going to get a lambda squared plus b lambda plus c equals 0. So the whole point here is that it seems like we were able to match up these coefficients between the two setups right there. So this is basically saying to us, in general, it's always going to work out that your characteristic polynomials coefficients are exactly equal to the second order constant coefficient linear differential equations coefficients. Let me just say this coefficients are guaranteed to match between second order diffie q and linear system. Right, so we can just do a little smidge of eigenanalysis in general of A, B's, and C's and see that it does work out that those match up there. So the point to me now is we can use this to help justify some shortcuts in our work. Right. So now if I say to you solve this differential equation right here, I can just jump immediately to my characteristic polynomial. Notice though that what this is going to do, so I'm going to tell you the good news and then the bad news and then the good news once again. The good news is I can just jump directly from my second order differential equation to its characteristic polynomial, skipping the entire convert to a system and do your determinant to your matrix and all that business. The bad news is that this is then therefore only going to tell us our solution in terms of x. But the good news is that when we get the solution only in terms of x like we got over here, we know that our other component of our system is just the derivative of x, so it's very, very easy then. So that's our bad news, that we only get x and not v, so we don't get our solution, our system solution. But we can just take one quick derivative because that's how our system was defined in the first place, our system conversion there. So we can actually recover that information back once again. So let's go ahead and do some quick examples right here. So it seems to me, by the way, I want to actually show one other little bit of smidge of shortcut up here. Another thing that you should notice is that every single time that we convert a system, or sorry, a second order differential equation to a system, we always get this 0 and this 1 as the A and the B within our A matrix right here. One of the things that that's always going to result in for us then is that our eigenvectors are always going to be of the form 1 lambda and 1 lambda right there, lambda 1 and lambda 2, right? That's always going to be the structure of our eigenvectors here, because we're always just taking the derivative of an e to the lambda t, and we're popping out an additional lambda. So that's why it's always going to be 1 and lambda 1 and 1 and lambda 2 right there, always for those choices. So let's see how quickly we can now solve one of these guys, or both of these, I guess I should say. In this case right here, I'm going to immediately go to lambda squared minus 5 lambda plus 4 equals 0. I'm going to see if this factors as lambda minus 4 and lambda minus 1 equals 0. I know that lambda equals 1 and 4, and so I think from here I can just straight up write my solution. I know that my solution then, my system solution even, is going to look like k1 e to the, I'm just starting to write lambda right there. Lambda 1 is 1, so it's just e to the t. What's our vector? Well, it's going to be 1 on top and then lambda 1 plus k2 e to the 4t, 1, 4, done. That's how little work it now takes us to find our general solution. Not only is this a very, very complicated calculus problem, we turned it into a little bit easier of a linear algebra problem, and now we get to even just skip the linear algebra because we showed the linear algebra problem is actually equivalent to a straight up 8th grade algebra problem. It's literally just solve a quadratic. It's all this actually boils down to, right? We keep on, we're just shaving off. We're not shaving off. We're getting out our garden shears here to give a haircut, right? We're chopping off massive chunks of our work that's required to do this. This still gets a little bit hairy if we get some kind of gross eigenvalues out here, so we can still do the same thing here. You know, lambda squared plus 4 lambda plus 13 equals 0. I recognize I can't factor it, so I got to go to my quadratic formula. Negative 4 plus or minus square root of b squared minus 4ac all over 2a. And what's that? Negative 4 plus or minus the square root of, that's 52. 16 minus 52 is going to be negative 36 over 2. And so that's negative 4 over 2 is negative 2. That's just 6i. 6i over 2 is 3i. So we kind of know automatically what our general solution should look like here for this guy. We know that we should be getting some y of t being our e to the negative 2t. E to the 3it is where we use our Euler's formula to get our cosine of 3t plus I, oh my gosh, can't write an I right now, plus I sine 3t, right? This is from our complex eigenvalue section right here. From this guy, I can expand this thing and get my two general components right here, to where I would then say, listen, we're going to take our real solution and our imaginary solution and separate those and use the linearity principle. So this is going to give me k1 e to the negative 2t cosine of 3t plus k2 e to the negative 2t sine 3t, right? That was because we said the real part is its own solution, the complex part is its own solution, and therefore we can take the linear combination of the real part and the imaginary part to find our general solution. Once again, if we want to then jump in, so again, notice that this is only, sorry, I'm miswriting a variable right here. Those aren't y's, those are x's. And further, if I want the solution, the system solution, instead of the individual solution for x, I can then go ahead and just take a derivative. You should just notice that the kind of crappy part about this one is we got to do a product rule for our derivative right here, but that's okay. I'm going to survive with that. I'm noticing that the k1 component and the e to the negative 2t component are going to match up top up there. So I'm going to write this as k1 e to the negative 2t. This is going to give me a cosine of 3t. And I need to leave, I think I need to, well, okay, I'm doing this a little bit All right, here's what I should do. Here's what I should do. Let me just write I was trying to get all this crammed in at the bottom down there. I should just do the math properly here. Our v of t should just be, I need to do product rules right here for both these to take my derivative, right? X prime of t equals v of t right there. So here my product rule is going to go ahead and it's going to give me, so what, I take the derivative of the negative 2t, so k1, all right. I'm trying to go fast here. Negative 2 k1 e to the negative 2t cosine 3t plus, now cosine of 3t is, we're going to take the derivative and we're going to get negative 3 sine 3t. All right, so on a negative minus 3 k1 e to the negative 2t sine of 3t. All right, that's our derivative from our first term right there. Now we're going to get minus 2k2 e to the negative 2t sine 3t, because that's the derivative of our second term where we took the derivative of the e to the negative 2t and we left the sine of 3t alone. Finally, we take get the second part of the product rule from our second term, which is where we took the derivative of sine and leave the e to the negative 2t alone. Derivative of sine of 3t is 3 cosine 3t. So I'm going to get a plus 3k2 e to the negative 2t cosine of 3t. And now what we can see is we can combine these guys into our overall collective solution right here, which is our y of t equals. And what I can see here is I can see that our x component, so every single term has an e to the negative 2t in it. Half of our terms have a k1 and half of our terms have a k2. So I'm going to use all those as my coefficients out here. So I'm getting my terms here that have k1s and e to the negative 2t's in my first grouping right here. It looks like that just gives me the cosine of 3t for the first group. For the second group, that gives me both negative 2 cos 3t, which is really this term right here, but with the k1 e to the negative 2t has been factored out. I am also getting, for this term right here, I'm getting my negative 3 sine of 3t. For my second grouping, all of these terms and this second term all have a k2 and an e to the negative 2t. So plus k2 e to the negative 2t, and this is times the vector. Our top component only had remaining a sine of 3t. And our bottom component had these two terms where, again, the k2 and the e to the negative 2t have already been accounted for. So it looks like I'm getting a negative 2 sine of 3t plus 3 cosine 3t. Running out of room. There we go. Crammed it in there, right? So always our imaginary solutions are going to be a little bit more work. But we still did chop out a huge amount of work that was associated with these guys by jumping straight to the characteristic polynomial. It requires us to then still take an extra derivative if we want to come up with our system solution rather than just our solution in terms of x. But that's not really too terrible. I mean, okay, you're going to have to do a product rule for all your complex stuff right there. That's not going to be the end of the world. Factoring out our common components right there, not the end of the world. So still much less work than we've been having to do for these. We keep on really massively reducing the amount of overall work required to do these. So this is good. We found that there's this general relationship that says anytime you're solving a second order linear constant coefficient differential equation, you can go ahead and jump immediately to your characteristic polynomial by just looking at the coefficients on your second order differential equation. And man, when we get real distinct eigenvalues, holy cow, is this like no work whatsoever right here. So notice, this is why I said, like 2 or 3 weeks ago, I said to you, I expect that we should be able to classify the behavior at the origin of any of these second order differential equations literally in our heads without writing out any amount of work. And that's because I now know that I can make this jump to the characteristic polynomial in my head. I know that I can factor a basic factorable quadratic in my head. I know that I can identify the roots of a factored quadratic in my head. And based on seeing these roots of 1 and 4, I know that we're going to be a source. We have real distinct eigenvalues. So source at 0, 0. Over here, very, very similarly, this one's a little bit tougher right here. I bet all of you guys could do this one in your head, but it might take you like 30 seconds of staring at the ceiling right here. The bottom line is, I know that this is going to be either a spiral sink, a spiral source, or a center. And what I can see, so a complex means it's one of those three choices. And based on the fact that our real component is -2, I know that this is going to be a spiral sink because the -2 for the real component says that we are decaying towards the origin. That's what that -2 is doing, is everything is decaying down to 0, 0. But we're doing so in a spirally fashion. Imaginary numbers are always helping us talk about rotation. So notice here that our ability to classify these is greatly improved by our ability to jump straight to that characteristic polynomial right there. So I would challenge all of you guys to always, every single second order differential equation that you see, you should say to yourself, can I just do the whole thing in my head? Can I literally classify the behavior at the origin without writing down any math? And I think that you guys can, because you guys are all masters of the quadratic formula by now, which is all this really boils down to. Right? So when did we even start discussing these second order differential equations in the first place? And the answer is this came up when we started talking about our harmonic oscillators, right? This was really a physics question, which is really where mostly everything in calculus originally came from. So let's recall what happened here. In this situation, we started by doing this like mass on a spring scenario here, and this is just one representative example. There's tons of things that are in a sense equivalent to this guy right here, but we had this mass on a spring, and we said this is our location at x equals 0. What we said to ourselves was to describe all of the forces relationship here, it should be that the force is equal to mass times acceleration. We started with Newton's second law of motion here. Then what we said was, well, listen, we know that our forces here are, we have two different forces that we want to be able to account for right here. And we said that our spring force is always a force that opposes position. The spring force opposes, what was the parameter that we gave on this one? I think we gave this spring force had a K on it, and it opposes position. Right? If you pull to the if the spring is currently to the right of rest, it wants to go left, and if it is to the left of rest, it wants to go right. That's how our spring force works. The other force that we had was our damping force, which we're thinking of as frictional force, and we know that the way frictional forces work is that they oppose, with some constant coefficient, they oppose velocity. If you're moving very quickly, there's lots of friction. If you're moving very slowly, there's not much friction at all. And friction is always in the opposite direction of motion. If the block is sliding to the left, then friction is opposing that. So friction must be a rightward force. It is the opposite direction of our velocity right there. So combining these two statements in here, what we can end up with right here is we have a spring force, is that this should be Fs plus Fd equals ma. And then we said, well, listen, I know how to rewrite all of these things in terms of their physics definitions here. This should be negative kx, negative bx prime equals m, and that's x double prime, because acceleration is the second derivative of position. And then we just typically move all of our terms to one side, and that's where we get our mx double prime plus bx prime plus kx is equal to 0. So this is what we define to be our general form of a harmonic oscillator. And we should notice one special little important thing right here, since this is our topic of conversation today. It's going to be the case that m is greater than 0. We're always going to have some amount of mass. We don't really talk about massless particles doing kind of behaving associated with forces here. The other thing that's true is that k is representative of our spring force. It's not a spring if k is equal to 0. By definition, springs have to have a k being greater than or being greater than 0 right there. If the spring force was 0, it's not a spring, it's a string, right? However, it is possible for us to have no damping forces out here, or at least theoretically. So notice that b is greater than or equal to 0, and that or equal to is important for our discussion here today, that it is possible for b to be equal to 0, whereas the other coefficients, we have to have those guys being in there. So what I want us to do then today is, rather than us spending our time focusing on classifying, like giving a name to the behavior near the origin where the equilibrium is located, like sources and spiral sinks, instead, can we come up with our classifications of harmonic oscillators? And that's kind of what we're going to look at with a little bit of our help from Python, a little bit of help from our math right here. So let's classify our harmonic oscillators. This is different from, but very closely related to, the act of classifying the equilibria at the origin of the related system, of the equivalent system. So the first one, the easiest one, is the undamped harmonic oscillators. There's no damping force, and remember that our damping force is the B term. This is how much damping is there. And so no damping is going to say to me, no damping says to me B equals 0. In that case, our general oscillator should simplify down to, from mx double prime plus bx prime plus kx equals 0, is now just mx double prime plus kx equals 0, right? Because b was equal to 0 in that case right there. And therefore, I can immediately go to solve some of the stuff right here. This is going to let me say m lambda squared. Now I'm going to write it not so stupidly. M lambda squared plus k equals 0. Well, m lambda squared equals negative k. Lambda squared equals negative k over m. And it looks like that means to me that we're going to get that lambda is going to be plus or minus I root k over m. So notice here we're always guaranteed to get complex solutions. And it seems like this is where we get complex eigenvalues. We know that complex eigenvalues are always going to lead us to one of three possible cases: a spiral sink, a spiral source, or a center. Spiral sinks happen when our real term A is negative. Spiral source happens when our real term A is positive, and a center, where we get closed orbit trajectories, is always going to happen when A is equal to 0, which is always going to happen in the situations where there is no damping force. Right here, right? So in this case right here, we refer to this, this term right here. We call this our natural frequency. Omega as the square root of k over m. And in this case right here, we can then pretty easily write our general solution for this guy to go ahead and look like our x of t is going to, well, okay, hold on, let me give myself a little bit more room right here. So we're always going to end up with our x of t is going to just be k1 cosine omega t plus k2 sine omega t. And you should notice that when we take derivatives here, we're just going to get a little change of trig function, change of positive negative, pop out an additional omega term right here. So our general system solution for position and for velocity should end up looking like our k1. The x component is the cosine of omega t. The v component, the derivative of x, well, the derivative of cosine omega t is negative omega sine omega t. Plus k2. The x component is sine omega t. The derivative of sine omega t is omega cosine omega t. And there we go. We got our general solution for every undamped harmonic oscillator is always going to look like this. So for our center is always going to be closed orbit trajectories. circles and ellipses. And we've seen these. We'll look at some more of them at the end, I believe, here. Or rather, I'm going to trick you with some of these at the end right here. So no damping is kind of our easiest possible case. It's a guarantee that we're always going to get. And again, notice that our k term has to be positive. If our k term could be negative, then this would be a positive number and we wouldn't be getting the I popping out. But remember that k and m both have to be positive, so this is guaranteed to be complex right here. I think that's another like little note worth throwing in right here. Right, so that negative sign right there didn't guarantee that we were negative. If one of our parameters was negative, then we would have actually had positive numbers, so the square root would have been a real eigenvalue, and we wouldn't have gotten complex solutions. But I know that in any physics scenario, k and m have to be both positive numbers based on the fact that these are defined to be our mass and our spring force right here. And so it's guaranteed that we're going to get the complex eigenvalues always, and it's guaranteed that we're going to get our real component is going to be 0 because of the fact that there is no damping. So that's sort of our simple case right here. Now let's go ahead and look and see what happens if there is damping. So if there is damping, what's going to end up happening? Well, we saw that we have our general equation of mx double prime plus bx prime plus kx equals 0. That's going to lead us to our, why can't I just write the m first? I don't know what's wrong with me. All right, there we go. It's guaranteed to lead us to this general quadratic right here. And that's going to tell me that lambda is going to be negative b plus or minus the square root of b squared minus 4a is m, c is k, all over 2m, which I'm going to write just a little less stupidly as negative b plus or minus the square root of b squared minus 4mk all over 2m. Right? These are going to be our eigenvalues that we're going to get out of this guy. So here's what we're going to end up seeing. What we know that we've been looking at in the last unit is that this overall thing right here is going to change behavior depending on the value of the discriminant, right? So discriminant, the discriminant is the value that is underneath the square root. And what a good word discriminant is. I find myself very often harshly judging things that are mathematically named. I love the word discriminant for this. It makes a bunch of sense to me because what it does is it discriminates between the number of real solutions that we have. If b squared minus 4mk is a positive number, then we're going to get 2 distinct real solutions. If it's 0, we're only going to get 1 real solution, and if it's negative, we're going to get 0 real solutions. We're going to get 2 complex solutions out there. So this discriminates between the number of real solutions. That's what its job is. So it's called the discriminant. I really like that. So if we end up finding that our b squared minus 4mk is less than 0, you guys know what's happening here in this case. If b squared minus 4mk is less than 0, then it's obviously going to be the case that we're going to get complex eigenvalues. Also, notice another feature of these is that there is damping. So that means to me that b can't be 0. Otherwise, that would be the no damping scenario. There is damping, right? That's what that means right there. There is damping. There is damping. B can't be 0. So notice here, b can't be 0. It was allowed to be greater than or equal to 0. So b is a positive number. So we're going to get complex eigenvalues. We're going to get that the real part is negative. That's the negative b over 2m. That's our real component of this because the I is going to crop out from the square root term right there. And so these are always going to give us a spiral sink, always. And the real question is, how do we classify these things based on, so this is our classification of the behavior at the origin right here. I really want to be saying is, how do we classify what type of oscillator this is? And in this case right here, we're going to give this the name of underdamped oscillator. So let's talk about let me give you guys my analogy for these ones here. So now that we've named one of these, an underdamped oscillator, I think that you guys have heard the words that are at least associated with some of these things otherwise. So I want to give you my analogy of what I think about when I think about oscillators. While I'm personally not necessarily a huge fan of these types of movies, I have seen a handful of them, and I've watched this scene happen in a bunch of, what do they call them, spaghetti westerns? Right. So the scene that I'm picturing in my mind, and even if you haven't seen any of these movies, I know that you can all like picture the scenario in your head, which is it's an old Western movie, and some cowboy goes riding into town on his horse, and he goes to the saloon, and what's the door to get into every saloon isn't it's not a door handle, it's not a door with latches, it's the double door, right? They have like the slats on it or something like that, and it's otherwise just like an open air door. And what happens is the cowboy comes in and he pushes that door open, and it slams open, and everybody in the whole bar, whole saloon turns around and looks, and the music stops and whatever, and the bad guy's there, right? But what I'm picturing for myself is that when you walk in and you push those saloon doors, what do? They swing open, they swing closed, they swing open, closed, open, closed, open, closed, and they settle down over time. Right? Now, if you are an engineer, then you're probably throwing up in your mouth at the thought of this door just sitting here just swinging needlessly over and over and over again. If you're an engineer, you should be thinking to yourself, wow, those hinges are going to wear out really fast right there. What we really, really like to see when we're thinking about things in an engineering perspective is, I want this door to work as efficiently as possible. If this door is doing 27 swings before it finally settles back down to its equilibrium rest state right here, then we're wearing out all these hinges way, way, way faster than we need to be, right? So this is referred to as an underdamped oscillator because the damping force on the hinges is not as extreme as it should be to cause the door to just close naturally, right? What would be the most efficient thing that's going to cause the least wear on the hinges is you push the door open, and I want it to just close right there. That would be the best, right? Now, what could also happen is we could introduce a whole lot of damping force associated with this door. We could just say, let's make that hinge so tight that it can barely move. And so this person comes in, he pushes the door, probably takes a ton of his strength, and it swings open. And then because we have so much damping force, the whole movie just pauses, and then boom, door is closed finally. That's ridiculous. We have such a high damping force on that thing that it took a really, really, really long time in that scenario right there for it to return to rest. So this is called underdamped because there's not quite enough damping for it to just return to equilibrium in a quick amount of time. On the other hand, you can imagine something being overdamped. There's too much resistance to the return to equilibria that even though we're not doing any wasteful swings back and forth, in an overdamped situation, there's such a strong damping force that we're just sitting there waiting for that door to return to closed for like a minute, right? And that's also not our most efficient thing ever if we're an engineer. If we're an engineer, I think that we kind of want to hit it right in the middle. If you're an engineer designing saloon doors in 1850, then your best case scenario is for that cowboy come in to slam that door open and it swings open, and what we want is for it to just return to rest quickly. Right? The least amount of time possible that it could possibly take to return to rest. What we don't want is any of the swinging back and forth settling down. What we don't want is so much damping that it takes 5 minutes for it to get back here. And even worse, the worst possible case is, what if there was no damping, undamped, then that means that you would just push it open and it would just stay open. Now the door never even closes. That's the undamped situation right there. So I've just described all 4 of the classifications that we're going to see with our saloon door, right? Undamped means you push it open and there's no force that encourages it to go back to equilibria. So it doesn't. Or perhaps in the undamped situation, you push it open and maybe that means that it just swings back and forth forever and it never actually attempts to return back to the middle. You've got to go and stop the door, right? That would be like our spring that we described. So again, I'm going to talk through all these again. In the underdamped scenario, there's not enough damping. It's underdamped. It hasn't been damped enough. So when you push it open, there's not enough damping force to cause it to just go back to equilibrium, and it does a bunch of swinging, extra swings. You can interpret those extra swings in the phase plane as us slowly spiraling towards the equilibria, remembering that our x-axis is position, our vertical axis is our velocity right there, there, and our velocity is constantly changing from positive to negative, our position is constantly changing from positive to negative, but those exponentials with those negative coefficients on them that we just ran across right here, those are guaranteeing that every swing of the door, it swings a little bit less and a little bit slower until eventually it's just sitting right there at zero. That's our underdamped oscillator right there. So the next ones that we should expect to see are our overdamped oscillator, where there's so much damping force that it takes like minutes for the door to close, or the perfect amount of damping force, where we're talking about the minimum amount of time possible for it to just get back to rest. Because if it goes too quickly back to here, it's going to swing past it, and then that's when we're doing the oscillations. If it goes too slowly, then it just takes forever, even though it doesn't do any oscillations. If we're engineers, what we're probably interested in is finding that sweet spot right there where we don't do any extra oscillations, we just go back to rest quickly. That's our perfect amount of damping, what we'll end up calling our critically damped case right here. So I just talked a lot. Let's go ahead and write out a bunch of these things that we just said right there. So our discriminant is discriminating between our three cases here, right? So our other case is that if b squared minus 4mk is greater than 0, then what you guys know is that if the discriminant here is positive, then we're guaranteed to get two distinct real roots. In this case right here, we're going to get sink, source, or saddle. Okay, sorry. In this case right here, based on, well, you guys are going to do a little bit of this math right here, but the fact is, I don't think that we're going to be able to get a source here based on some sign issues. We're not going to get the positives and negatives to match up to ever give us a source in this case right here. So what I think is going to happen is we're just going to sink towards the origin right here. And so I think that I could say that this is just a regular old sink, and that's our classification at the origin. And that this is going to be giving us an overdamped situation here. This is when there's more damping than there needs to be for that door to return to rest. All right. So finally, in the case that engineers are primarily interested in, if b squared minus 4mk is equal to 0, then what you know that we saw when we did this last week is if we get this discriminant to be equal to 0, then you get repeated eigenvalues of negative b over 2m. Negative b over 2m. Notice that this is guaranteed less than 0. Guaranteed to be negative because b and m are both required to be positive right here. And so it seems like this is going to be our degenerate sink. That's our classification at 0, 0. Oh, I see what I'm doing. And this is what we refer to as being critically damped. And notice a cool thing about this. A cool thing about this is that I could say to you, hey man, listen, I'm trying to build a door and I'd like the door to experience critical damping. The door is going to weigh 10 kilograms and it's going to have a damping force of, or I might be able to say there might be some of the spring that's returning the door to the beginning, or excuse me, there's going to be a damping force with the hinges of B being 6, and then you could say, how much spring force do I need so that I can experience a critically damped door. You could then solve for the K that would be necessary in association with the M and the B for you to experience a critically damped oscillator, where we're going to experience the least amount of time it takes to get to the origin. Now, this word critical right here, you should recognize a place in calculus. You've seen this before. A critical point, or a critical value, is a location where derivative switches positive negative. And you should notice that a critically damped oscillator is the I'll just say where right? And how do you switch from positive to negative? It's UB0, right? So a critically damped, I really, really like that name for that right there, because it matches our previous intuition from calculus about a critical value or a critical point being a location on a graph where we are potentially at a maximum or a minimum. It's where a slope is either equal to 0 or undefined. Very, very similarly, critical damping is where our discriminant is equal to 0. It's the transition place between the positives and the negatives out there. So cool. So we can talk about the classification of all of these things right here. So what I feel like, so, you know, our four classifications that we're going to end up seeing, and I have all these written out again at the end out here, is our oscillator can have no damping, where B is equal to 0. The damping term is equal to 0. In this case, because there's no damping, we expect it to just oscillate forever with no decay in amplitude, and therefore our classification at the origin will always be a center. It's not going to spiral in or out. If we get that our damping force is not as extreme as the mass times the spring force right there, then we're going to end up with our oscillator where we don't experiencing enough damping for it to just settle down quickly, and we do lots of this oscillating back and forth as the amplitudes decay. That gives us those spiral sinks in association with our underdamped oscillators. When we have a ton of damping force relative to our spring force right here, that's when it's going to go really, 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 really slow in its closing right there. It's over. There's too much damping for that door right there. It's taken 5 minutes to close. My other analogy that I like to talk about with this one is there's this stupid experiment that's been going on at I think it's some university in the southeast U.S. somewhere, where a professor set up this experiment something like 100 years ago or something in the ballpark of that, to where what he did is he put a bunch of pitch. So if you know what pitch is, it's basically like tar, but it's like this waterproof tar. It's like basically stuff that people used to patch boats with back in the day, right? So you make a big ship to sail on the sea. It's really just a bunch of wooden planks next to each other. You seal it with pitch because it's this like really, really, really thick resin. And pitch is something that's one of those objects that sort of, it feels like a solid. It's like really, 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 really firm clay. It's almost like it's a solid, but it sort of acts as like a liquid. And so what he wanted to do is to measure the viscosity of the pitch, is he put a bunch of it into a funnel, and he's waiting to see it drip down, right? So what happens is he put this pitch into a funnel. Well, it turns out it's only dripped 7 drips in like 90 years or something like that. It's dripping at an average of like 1 drop drips off like every 14 years or some. I'm sure I'm messing up some of my time, but I'm on the correct time scaling right here at least. And the funny thing is that they set up a camera to, so now we're in the modern day where there's like cameras and stuff. So some grad students so this is like an experiment so this has like the record for like the longest actively running scientific experiment ever or something like that, because it's been going on for like 90 years measuring the dates of these drips. And obviously, though, it's affected by things like the temperature inside of the building and stuff. So they've like tried to maintain the temperature in the building according to historical temperatures and stuff. And they've more recently set up a camera to make sure that they monitor the thing. Well, what ended up happening was the camera got like turned off over spring break or something like that, and a drip ended up happening. So they missed like a 1 in 13 year drip happen, and they have to like wait 13 years to like observe the next drip, which I find to be hilarious right there. But that is a case of extreme damping right there. It's almost a solid. It's technically technically a liquid because it'll drip, but it takes 13 years for one drop to drip through the funnel right there. So that's also a thing that I picture saloon doors and tar in a funnel. I think that's kind of, you can tell I'm not an engineer. But in any event, that's our over damped situation right there, is it's just going insanely slow. Our perfect amount of damping to experience the least amount of time required. So this is our minimizes the time to get to the origin. Or time to equilibria, I should say, more generally. Is when we have that critically damping, where we get that discriminant being exactly equal to 0 right there. So there's our classification. So in general, our classifications are underdamped, or sorry, undamped, underdamped, overdamped, critically damped. And I'm going to talk through them all again, because these matter. In an undamped situation, our system is just going to oscillate at that natural frequency, that omega that we talked about, and the amplitude's never going to change. It's just going to experience those same orbits forever until acted upon by an outside force. This undamped case is a little bit of an idealized situation. Nothing experiences no friction, nothing experiences no air resistance, but it might be the case that there's essentially none, like almost none. We're going to look at that example here in one moment. In an underdamped case, there's not a lot of damping force. So things are going to experience some oscillation, but they're going to eventually tend towards 0 gradually. In an overdamped situation, a system does return to equilibria and it doesn't do any oscillator, right? This is where you push the saloon doors open and they just slowly closed. So notice it didn't do any oscillating. It just opened and closed. It turns out that some overdamped systems do experience a crossing over x equals 0 or v equals 0. So in those cases, it sort of looks like it did like a smidge of oscillation. That can happen in an overdamped case, but literally once. You will only ever cross an axis at most one time in any graph of any overdamped oscillator. Finally, our critically damped scenario is where the system returns to equilibrium as quickly as possible without oscillating. And you should notice, what we are not suggesting is that it takes the physical shortest distance to get to equilibrium. It takes the shortest amount of time to get to equilibrium. That's the thing that's getting optimized in our critically damped scenario. So to wrap up today, all I want to do is talk about some sort of like warnings as to what we want to see when we see these graphs out here. So the two types of warnings are comparing undamped and underdamped, and then comparing critically damped and overdamped. So let's look at these two like kind of pairs together right here. So undamped versus underdamped. Remember that what we should expect to see is, with no damping, you should expect to see closed orbits. With underdamped, you should expect to see spirals, right? So these are really generally really easy for us to identify. Closed orbits versus spirals for undamped versus underdamped. You see a spiral, it's an underdamped oscillator, period. If you see a perfect closed orbit trajectory, it is experiencing no damping, period. Those are pretty easy to identify visually. The only risk that's associated with these, with misclassifying these based on a graph alone, is when we do have damping, but very, very little damping right here. So there's a minimal damping force right there. Let's go ahead and take a look and see what we get in our Python solutions when we do have a harmonic oscillator with that does have damping, but has a very little damping right here. What's the graph? And you should stop and you should say to yourself right now, this does have damping. So I know to expect it to look like a spiral. Because why might you confuse a spiral with a closed orbit trajectory? Let's go take a look. So over here, we've got our beefed up grapher right now. This is the thing that I sent off to you guys here. So what we're going to do is we're going to import our required libraries right here. Obviously, what our job is to throw in the appropriate coefficients right here. So when I do my A, B, C, D right here, these are referencing my A matrix, right? So notice that what I've got to go do for myself now is this is a great opportunity for me to go and scroll back up and recall that general A matrix that we're always going to get. This guy that looks like this. So 0, 1, negative C over A, negative B over A. Wait, I think I just got those backwards, right? The C comes first and the B comes second. Yes, negative C over A, then negative B over A. And notice there's definitely some like variable naming confusion here because we've been calling our A matrix having values of A, B, C, D, but I'm now using A, B, C as my coefficients on my second order. So I understand that we're kind of doing probably some abusive notation, I believe is what they call that there. So negative C over A is just negative 1 over 1, so that's just going to be negative 1. Our negative B over A looks like it's going to be negative 0.001. So it looks like that's the A matrix of consideration associated with the second order differential equation. So now let's go back to Python and do this. 0, 1, negative 1, negative 0.001 is what we want to graph. 0, 1, negative 1, negative 0.001. And let's go ahead and run this whole dang thing. So I'm going to import my libraries. I'm going to define my functions and coefficients, initializations, forwards time solution, backwards time solution, generate the graph. And what we're getting right here is you should be a little concerned right now. What it looks like I just got is closed orbit trajectories, despite the fact that I know that we're experiencing damping. Why did I get closed orbit trajectories? Well, maybe this is damping so little that the spiraling inward is happening so slowly that in the duration of time that we graphed our solutions for, we didn't go out far enough in time to see that this thing actually was experiencing the decay towards the origin. I didn't get to see it right here. This looks like closed orbit trajectories to me, but I know that we had damping. I know that this should be spiraling inwards. So what I'm going to go say to myself is, wait a minute, how much time did we graph this thing for? Oh, well, we only looked for 5 seconds. Let's make it 100 seconds. If I do 20 times as much time, hey, so now I can see, okay, and by the way, why do I have my... The thing that's slightly bothering me right here is that I feel like I have the wrong signs on some things because it looks like from here we're actually moving outwards instead of inwards. But the point is that we clearly are spiraling right here. We were just spiraling really, oh, I see. These are the, no, never mind. Anyway, the point is it is doing that motion right there, but we have to graph this for a longer duration of time. And so kind of my like takeaway on this one is closed orbits and spirals might look really similar to one another because remember, a closed orbit is where two trajectories are going to come together and actually match. A spiral might be where two trajectories come almost together but like miss each other just barely there, right? And the more barely it is associated with smaller and smaller dampings out there. So when we have these differential equations that do have damping but have minimal amounts of it, if you only graph it for a short period of time, then you're going to end up experiencing something that looks like a closed orbit trajectory because you just couldn't see the change in amplitude that was associated with the spiraling. So in these cases, it's a little bit more practical to graph these for longer durations of time out there. So by extending our time, we got to see that there was a change in amplitude over time out there, which we see, but this is just a bunch of like lines, like basically almost overwriting each other right there. The other thing that's kind of risky right here is that we know that every graph is going to have some error because it was computed numerically using one of our techniques out there, Euler's method, Runge-Kutta 4. We used Runge-Kutta 4 for that one right there. To form a perfect true closed orbit associated with undamped oscillators, there literally has to be no error, right? These two things literally have to come and like overlap back over a top of one another again. If we have literally any amounts of error, they're going to slightly miss one another. So the other thing that's going to be kind of the case here is you should pretty much always be a little bit skeptical of numerically predicted solutions when the graphs look like closed orbits, because you should really say to yourself, or excuse me, when they look like spirals, because you should say to yourself, did the spiraling happen because it was supposed to, or did the spiraling happen because of the numerical error in the predictor out there? So it's the spirals that you got to worry about. If it really does look like a closed orbit out there, that's when we should say to ourselves, well, as long as we graphed it for enough time, we would have seen the spiraling happen right there. But just recognize how close a closed orbit is to a spiral and say to yourself, if you see one of them, you should have like some things where you're saying like, well, why might this actually be the other thing that I think it is? If it looks like a closed orbit, why might it actually be a spiral? Because you didn't graph it for a long enough time. If it looks like a spiral, why might it actually be a closed orbit? Well, maybe you're using a numerical solver that has high amounts of error, and our error off of a circle is going to give you a spiral. So the misleading thing could go both directions. So you see a spiral, could have actually been supposed to be a closed orbit if there was error. if you see a closed orbit, it could have actually been supposed to be a spiral just because you didn't graph it for a long enough time because maybe it has only little bits of damping out there. Right? So that's one of our things that we should like watch out for right there. The other thing is that critically damped and over damped graphs can look very similar because they're both just going to essentially go to the origin. What we should do is let's go ahead and take a look at the graphs of each of these two things and then remind ourselves that we can pretty easily see our mathematically distinguish between which of the two cases it should be. So once again, I kind of want to use this idea right up here to get my A matrices for each of these guys right here. Here I'm seeing that A equals 1, B equals 5, A equals 4, A equals 1, B equals 4, C equals 4. I don't know why I drew an A for the next one. I was getting ahead of myself over there. That's a C. And so we can say that our A matrix, again, is going to be our A matrix in this case is always going to be 0, 1 up top. It's going to be negative C over A, so negative 4 for this one. It's going to be negative B over A, so it's going to be negative 5 for this one. And therefore, our A matrix for this guy should be 0, 1, negative 4, negative 4. So let's go ahead and take a look at these two graphs right here, see that they're going to be similar to one another, but that we can be positive about the distinction between them by doing just a bare smidge of algebra right here. So 0, 1, negative 4, negative 5. I don't need to go for 100 units of time. Let's back that back down. I think this 5 has been working out pretty much fine for us here. Sorry. Here we are. 0, 1, negative 4, negative 5. So it's the first one. I'm returning my time upper bound to just 5 seconds right there. And I'm actually thinking that maybe I don't want all of these initial conditions on this thing right here. Maybe let's just pick like one initial condition at 1, 1. I think let's do the single initial condition right here. So I'm going to comment out the list of them and just do the single. And so here is our one trajectory that's associated with this. We can see it is just going to the origin right there. It is doing a single swoop. You should see it did cross one axis one time. That's something that we expect may happen right here. I'm going to go ahead and screenshot this one and throw it into our notes. There's that one. And now let's go ahead and do the same thing, but the only difference is that that negative 4 becomes a negative 5. So now back here in Word, the thing that was the negative 5 is now a negative 4 over here, right? The negative 5 is now a negative 4 for our other one. That seems like a very, very nearby system. It seems closely related to this one, right? So let's pop back over here and swap out this negative 5 for a negative 4. And we're still doing the exact same initial conditions so that we can make our comparison between these two. And we can see we're getting a graph that looks very, very similar. So if I just showed you these two graphs, it's very hard for you to make the judgment about which is actually going to be which, right? These look super closely related to one another right here. Right, super closely related. And I feel like I can see the difference, barely. I feel like let me click, dang it. I feel like I can see the difference right here, which is that this one seems to have a sharper bend right there, and that one seems to be a little bit swoopier. I feel like this one looks more linear as it approaches the origin, and this one looks a little bit less linear as it approaches the origin. But holy cow, are these two things outrageously closely related to one another. But what I think I can do here is I can go do my comparison of the discriminants. So let's say look almost identical. Compare discriminants. Well, we had that our mx double prime plus bx prime plus kx is equal to 0. Our two scenarios here were plus 5x plus 4x, So we had that our discriminant term was going to be in general, our discriminant was b squared minus 4mk. Right? So it looks like here we're getting our discriminant to be, so b squared is 5 squared minus 4 times m is 1 times k is 4. And so here we're getting 25 minus 16, and that's going to give us 9. On the other hand, over here, we're getting our b squared, our discriminant, is equal to b squared. Wait a minute, don't I want my... Because am I not getting a discriminant of non-zero for both of these? 4mk? Oh, well, 1. I wrote this one wrong right here. That's a 4. Oh, yeah. Okay. That's why. I like panicked right there, and then it's because I was being stupid. B squared minus 4mk. And it looks like this is 16 minus 16, which is 0. So here, discriminant is greater than 0, means we are overdamped. Here, our discriminant equal to 0 means that we are critically damped. So the point is, you really can't just look at one graph and see what the difference is going to be right here. Obviously, these two solution curves look so almost identical. The issue is that technically speaking, this one is taking less time to get back to the origin than this one is taking. But you can't see time on these graphs. You can only see your x and your y components right here, right? So the point is, can we just use graphs to classify our oscillators? And the answer is sort of, almost, sometimes, mostly. Right? If it's undamped versus underdamped, I mostly can identify those. If I see an obvious spiral, then it's underdamped. If I see an obvious closed orbit trajectory, it clearly has no damping. But this overdamped versus critically damped scenario right here, really tough to make that judgment between the two right here. Here's our two particular solutions through 1, 1. They look almost identical, but by checking out a little bit of our discriminant math right here, we can see that we're going to get an overdamped versus a critically damped scenario right here, showing me that this one must be taking less time to get to the origin. And even though, and I mean, look at this trajectory. I even feel like the length of this trajectory maybe looks longer than this one, like the arc length of this versus the arc length of that, but that's not what we're measuring. We're measuring the amount of time required to get that green dot to 0 right here. This one's going to get to, and maybe we want to pick like a neighborhood about the origin to enter within. This one should be doing it faster. That's what critically damping is going to do. This one's going to get there, but it's going to go slower. Finally, this is the one other thing that we wanted to see here today, which is that even in our over-damped scenarios, remember what we said about the over-damped was that it's going to return to the equilibrium without oscillating, but it might be that it crosses over x equals 0 or v equals 0 once, and you can see that we did cross over the line v equals 0 once. There was one crossing of one axis can potentially happen in an over-damped situation right here. That is possible, or in a critically damped situation here as well. So those things can occur. Yeah. So there we go. So now we've managed to not only classify the behavior near the equilibrium of each of these things. So we've now got sinks, sources, saddles. We've got spiral sinks, spiral source, and center. We got degenerate sink and degenerate source. We got star sink and star source. We got Yeah, I think those are the 10 classifications that we've seen so far. We're still going to give a few more names to some other things, but what you guys should see that we're doing in our very next video here, section 3.7, the trace determinant plane. What we're going to do is we're going to identify two linear algebra terms, trace and determinant, and what we're going to see is that these classifications of behavior near the origin, we're going to make this literally even easier than it already is right now. So this should have been easy enough. You should be looking at this example right here and being like, damn, we have really simplified this down into almost nothing. We're literally going to make this even easier for ourselves, or I should say, we're going to get things that are even easier than this, but in terms of our systems rather than in terms of our second order differential equations. So we're going to get an epic shortcut like we got here and associated with the trace determinant plane up there. And again, as it's going to boil down to, all of the most important math we're doing in this chapter is actually happening just in the quadratic formula here, right? Which is kind of ridiculous. But this is the types of arguments that we're going to be making in section 3.7 with the trace determinant plane, and that's what we're going to pick up with here next week. So pretty heavy couple weeks right here of getting all of our classifications of systems. But now what we're going to be able to do is we're going to be able to expand our minds a little bit. What we've got coming up here in the future is we've got things like, what happens if this is not 0 over here? What happens, and that's for our second order differential equations. Other things that might happen. What happens if we have a system of linear equations that aren't actually linear, just this general system of differential equations where we might not have constant coefficients? What happens when we come up against second order differential equations where we don't have constant coefficients, so we can't just use the, oh, it's the same thing as the characteristic polynomial setup right there? And what happens if we get stuck doing the calculus? So what we're going to do is we're going to be spending the rest of the semester expanding on our two primary setups right here, which is what happens in a more general version of a second order differential equation. What happens if we don't have constant coefficients? What happens if it's not equal to 0? What if there's just like sine of t is sitting right there for 0? Then what do we do? And again, what happens if we end up in some more difficult system settings where it's no longer a constant coefficient linear system? So the reason that we are like going nuts on this highly specific scenario of linear constant coefficient systems or second order differential equations is because we want to use that as our like cornerstone from which to build off of. So we say, oh, what happens if we change this? And we'll see it's just an alteration of what we've been doing. What happens if we change this other thing? Oh, it's just a different alteration of what we've been doing. So this is sort of our like core base case foundation right here. And now we're going to kind of take a look at all of the things that are not all the things. We're going to take a look at three broad things surrounding this that are variations on these things. And that's what we'll be covering here for the rest of the semester. So that wraps up section 3.6, our second order linear differential equations here for the day. And I will see you guys next week for section 3.7, the trace determinant plane, where we're going to get a pretty epic summary and some really nice diagrams summarizing everything that we've seen for the last like month and a half right here. I'll see you guys for section 3.7, the trace determinant plane, next week. Have a good one.